Hey, thank you very much for the invitation. I'm very happy to visit IIS. And today I'm going to talk about conformally invariant fields out of Brownian loop soups. And this is based on works in progress joined with Antoine Gigot from EPFL and Titus Lupu from CNRS. So I will first give some background on Brownian loop soup, and then I will discuss our construction of conformally invariant field in a measurable way from this loop soup with any subcritical intensity C between 0 and 1, and also i.i.d signs given to each cluster. So first, the background review. As you know, the Brownian loop soups have been introduced by Lawler and Werner, and they first defined a measure on Brownian loops by the following explicit integral. So this is just integral on rooted loops, where Z is the root of the loop and T is the time duration of the loop. And this PZT is a probability measure on two-dimensional Brownian bridges with time length T and root Z. And then this PTZZ is a real number. It is the weight, which corresponds to the transition density of the Brownian motion in dimension 2. And with this definition, they define, actually this measure can be defined in any dimension D, but we will be interested in dimension 2. And you can also see that this measure has total mass infinite, but because, for example, when T is very small, this integral explodes at T equal to 0. However, this measure is locally finite if you restrict it to T away from 0 or infinity. And then Lawler and Werner use this measure to define the Brownian loop soup to be a Poisson point process with intensity C times mu, where this C is also called the intensity of the Brownian loop soup. Here I show you a simulation. And in fact, we can, for any domain D in the plane, we can also look at the loop soup restricted to this domain D, which is also equal to a Poisson point process of intensity C mu D, where mu D is mu restricted to the domain D. As you can see here, when D is a bounded domain, then there are almost surely finitely many big loops in this domain. When I say big, I mean either time length or diameter greater than epsilon. And
always made it up to
is there any question?
Maybe someone didn't mute.
Oh, mute. Okay. Okay. Sorry. And you can see that there are almost surely infinitely many small loops in of course, this picture is only a discrete approximation, but actually the picture is dense in the domain because around any given point, there are almost surely infinitely many small loops surrounding that point. Okay. And also, fundamental property of the Brownian loop soup is that it is conformally invariant. This is because the Brownian loop measure was defined to be conformally invariant. So if we take a Brownian loop soup in one domain D1 and then map it by a conformal map to another domain D2, then what we obtain in D2 is again distributed as a Brownian loop soup in that domain. And then once we have the Brownian loop soup, there is a notion of clusters which are defined to be the connected components formed by the Brownian loop soups. So two loops are said to be in the same cluster if there is a finite chain of loops that connect them to each other. And it was shown by Sheffield and Werner that there is a phase transition at the critical intensity C equal to 1, so that if C is greater than 1, then in domain D, say the unit disk, there is almost surely one single cluster. And if C is smaller or equal to 1, then this loop soup will almost surely form infinite many clusters. So as this picture I show you is a subcritical or critical regime where you have infinite many clusters. And they have also shown that if we look at the outer boundaries of the outermost clusters in this loop soup, then this is a collection of simple loops which is distributed as a conformal loops ensemble, CLE. So these red loops are distributed as CLE. And there is a one-to-one correspondence between C, between A third and 4, kappa between A third and 4 and C between 0 and 1, right? This. Okay.
In particular, just to understand the clusters, none of them goes to infinity if it's done on the full plane.
So in fact, if you are in the full plane, then I think there is an infinite cluster. So there are infinite many loops, big loops, which will go close to the origin. So you end up just have one cluster.
This is for any C, in fact, or?
Yes. I think Temse is correct. So it only makes sense to look in some domain which is not the full plane. So usually we look at simply connected domains. So now I'm going to another aspect about the Brownian loop soup, which is focused on the local time field of the Brownian loop soup. And there is an isomorphism theory, which was initiated by Symanzik and Brydges-Fröhlich-Spencer and Dynkin, where they studied different versions of isomorphism relating the occupation time of Brownian motions to random fields. And then Le Jan also extended it to the case of Brownian loop soups. And he has shown that the occupation time field T of Brownian loop soup with the critical intensity C equal to 1 is equal to 1/2 times the square of the Gaussian free field phi. This 1/2 is due to the convention on normalization. I will possibly be quite loose in the following and sometimes forget the 1/2 when I talk about isomorphism theory. In fact, so this isomorphism for Brownian loop soup, Le Jan showed it holds in the continuum Euclidean space in dimension 1, 2, and 3. And it also holds for random walk loop soups with exponential holding time on any most discrete graphs. And in fact, when D equal to 1, or if we are on a discrete graph, then the occupation time field of a loop soup is finite on any point of the space, and it is directly well-defined as a function. And also the Gaussian free field is finite, and so this isomorphism can be just understood in the literal sense that you can take the square of the Gaussian free field and get the occupation time field. However, we were mostly interested in the continuum case of dimension 2, where we actually need to renormalize to make sense of this isomorphism theory. So as
question.
Yes.
They mentioned 4, it is just due to things not being well defined. So it's not that there's an inherent reason that this doesn't hold in high dimension.
Yeah, on higher dimensions, the square of the Gaussian free field, as I know, is not well defined. Like the weak renormalization works up to dimension 3,
But on any discrete graphs in particular,
Yeah, in any
graph that
discrete-
kind of approximates 4 dimensions, it still holds.
Yeah,
because it's
exactly.
multidimensionality is helpful.
Yes, it's, yeah, exactly. Even high dimension discrete graph. Yeah, it works. Yes,
Since you mentioned discrete approximations,
yes.
is it the case that in the scaling limit there will be many discrete loops which drop out of sight because they do not reach macroscopic size? And in that case, what happens to the local times? Does it scale away?
So is your question like for any dimension in general?
Any dimension.
Yeah, so the small loops in the discrete, they disappear in the scaling limit.
And what happens with the local time?
Yeah, and also the local time in the continuum, I think they do not depend on these very small loops, possibly because there is some law of large number around these small loops. And for example, in dimension 2, anyway, in the continuum, this definition, we take away the small loops when we do the renormalization. So the small loops, like, yeah, the small loops don't have an effect.
Thank you.
Mm-hmm. Yeah, so exactly, just directly corresponding to your question. Yeah, I want to say in dimension 2, in order to make the local time well defined, because due to the presence of infinitely many small loops, the actual local time is infinite. So in the continuum, so in order to define it, we need to first throw away all the loops smaller than epsilon and look at its local time, and then take away the expectation, and then let epsilon go to 0 in order to get a scaling limit.
Yeah, thank you.
So this is a way we define the renormalized local time field in the continuum. And a different way to give the same definition is we can also look at the characteristic function of this integral of the local time field with any function f, and it is given by some this formula of integral where mu is the measure on Brownian loop, and the TL is occupation time field of one Brownian loop. So on the other side of the isomorphism theory, we say the local time is equal to the square of the Gaussian free field. So for the square of the Gaussian free field, we do the usual renormalization procedure called the Wick square. We also take the square of some modified version and take away the expectation and then take the limit. So these two renormalized versions of local time and Gaussian square of Gaussian free field have the same distribution. So this in the continuum 2 dimension, we need to do all these renormalization, but which is rather inconvenient. So Lupu has introduced a cable graph system which serves as like an interpolation between the discrete and the continuum. So he looks at like a discrete graph for example Z2, which approximates the 2-dimensional plane, but where each edge is considered as a continuous interval, and the loop soup is does a 1-dimensional Brownian motion on the intervals, and they at the vertices they just go to one of the 4 neighbors with probability 1 false, and with this on this cable graph, this loop soup is locally dimension 1, so the occupation time field is a finite function, and so we can take the square root of this occupation time field, and so he has shown that the isomorphism still holds on this cable graph. Okay. And then, so on this graph, because the graph is composed of continuous edges, so we can actually see the different clusters of the loop soup. So here I represent by different colors just some possible configuration of a loop soup on this cable system, where one cluster I draw it by one connected component with the same color. And once you have a Brownian loop soup and its occupation time field, you can first take the square root, and loop will show that you can then give i.i.d plus or minus signs to each cluster, and in this way you recover a Gaussian tree field on this cable graph.
And again, the cluster is the connected component of the loops. It's not a single connected component.
Connected components, yes. So it's a collection of loops which overlap each other.
So exactly the difference between clusters is where the occupation time is 0.
Yeah, exactly. So on this graph, because everything is finite, so you can see where the cluster stop and give i.i.d signs. So this allows one to recover the Gaussian free field as a measurable function of the loop soup on this cable graph and also the signs of the clusters. However, this procedure cannot be carried out directly in the continuum dimension 2. Okay, one natural question is to ask whether we can also recover the Gaussian free field as a measurable function of the Brownian loop soup and i.i.d signs in two-dimensional continuum. And naively, if you want to directly apply this method, then it cannot be carried out because in the continuum we have renormalized all the field, and the local time is not a positive function, etc. And also, like the local time and the Gaussian free field, both they are not functions, but they are distributions. They do not have pointwise values. And another natural question, which is more difficult, is to also find an analog of isomorphism for loop soups at subcritical intensities, say smaller than 1. And this, there was no results, like even on the discrete graphs. So now with this background, I can now present our construction of conformal fields in a measurable way from a loop soup with intensity C between 0 and 1, and i.d signs of the clusters. So our construction uses the multiplicative chaos of the Brownian loop soup as an important tool. So a measure of beta A on A6 points of one Brownian motion have been introduced by Bass, Brydges, and Gaussian in 1994, and also more recently, i.i.d, and Shi have shown that it is also equal to some other notion of A6 points. And Jago in 2020 has constructed the measure of multiplicative chaos for one Brownian motion, which is like taking the exponential of gamma times the square root of local time of that Brownian motion. It has shown that this multiplicative chaos measure is in fact equal to a constant multiple of this beta A measure on A6 points. And then Jago has also extended this measure to multiple Brownian motions. And more recently, i.i.d, Brydges, Jago, and Lupu have constructed the multiplicative chaos measure of the Brownian loop soup for any gamma between 0 and 2, And intuitively, this multiplicative chaos measure should be thought of as constant times the exponential of gamma times square root of the local time of the field. Even that, it doesn't directly make sense in the continuum because the local time is infinite field. So now I'm ready to present our construction. And just for some reason convention, I will use the parameter theta equal to C over 2 for the intensity. So that's the intensity. Critical intensity now is theta equal to 1/2. It's just a question notation. And we also changed the normalization of this multiplicative chaos measure in a way so that the expected density of our multiplicative chaos will be constant, equal to 2 at each point. And then what we do is that we give i.i.d signs plus and minus 1 to each cluster with probability 1/2. And then we define measure m gamma plus to be the measure m gamma restricted to the clusters which take plus sign. This restriction makes sense because the multiplicative chaos measure is supported on 6 points of the loop soup. And so every m gamma typical point is visited by a loop. So if we restrict the measure to clusters, we don't get 0. Okay. Then we define a field h theta gamma in this way. We take the m plus gamma measure and take away its expectation, integrate over fx and divide by some renormalizing constant c gamma theta. Okay. And so we show that, so our theorem is that for each intensity between 0 and 1/2, for any bounded measurable function f, this integral h theta gamma f converges in L2 as gamma goes to 0. And moreover, this convergence can be lifted as a convergence of the field h theta gamma in the Sobolev space h minus epsilon. And we also show that this normalizing constant, the correct normalizing constant, has this asymptotic behavior gamma to the power of 2 times 1 minus theta as gamma goes to 0. So I want to emphasize that this field h theta, by definition, is a measurable function of the Brownian loop soup and the size of its clusters, because it's defined from that multiplicative chaos and multiplicative chaos. And the reason why we define this field and we are interested in this field is that we believe it to be the canonical candidate for the isomorphism theorem for all theta between 0 and 1/2. So I will give more justification on this isomorphism part. So let me first give you the special case of theta equal to 1/2. In that case, the field h theta will have the law of a Gaussian free field in the domain. And also, so in particular, this will be a measurable function of the loop soup together with the i.i.d signs of the clusters. And also the plus multiplicative chaos measure will be equal to a normalized version of exponential of gamma h. And the total multiplicative chaos measure will be equal to 2 times the hyperbolic cosine of gamma h. And then this normalized local time field of the loop soup is equal to 1/2 times the square of the weak square of this Gaussian free field. So I just want to note that our loop pool and the CPU beta, they have obtained in some other unpublished work that they can also recover the Gaussian field in a measurable way with respect to the loop soup and the signs of the clusters, so that the Gaussian field squared is equal to the local time field with some different approach.
And in that, their approach is also not for the subcritical case.
Yeah, it's only for the critical case. Yeah. So our approach works for all theta between 0 and 1/2. And I first concentrate on the critical case to show that it is a correct candidate for isomorphism. So let me stay a bit more on this theta equal to 1/2 case. In fact, in the work by i.i.d, Tiki, Jago, and Lupu, they have already shown that the multiplicative tails at the critical intensity is equal to the hyperbolic cosine of the Gaussian field. And the intuitive reason is very simple. It's because it should be thought of the exponential of gamma of square root of the local time field. And by isomorphism, local time field is like the absolute value of the Gaussian field. So it will be like equal to the hyperbolic cosine. And they actually showed it from taking the limit in the discrete where everything is exactly true. So in our case, for the critical, at the critical intensity, what we prove in addition to this result is that you can further restrict the multiplicative chaos measure to the positive and negative clusters, and the restriction is exactly equal to the E gamma H or E minus gamma H. As I said, we have a slight change of normalization for the multiplicative chaos. And so this is also corresponds to a change of normalization of the exponential gamma H. And our normalization is 1, so that the exponential gamma H is equal to this surface expansion in terms of the weak powers of H. So like this is kind of the correct normalization that we want to use. And once with this series expansion and the fact that M plus is equal to exponential gamma H, you can see that it is natural to define H as a limit when gamma goes to 0 of this M plus minus 1. So it should, this tells why this definition will give us the correct Gaussian field in this case. And I recall that for all theta between 0 and 1/2, we have defined our field H theta as some limit of M gamma plus minus 1 over some normalizing constant Z gamma theta. However, for theta not equal to 1/2, it is in fact not possible to write this multiplicative chaos in terms of this sum of exponentials. So the subcritical case is much more complicated. So let me now give more properties of this our field H theta for all subcritical intensity theta. We show that this field H theta admits a covariance function C theta, and that covariance function C theta explodes on the diagonal as log 1 over x minus y to the power of 2 times 1 minus theta. And this power, as you see, if theta is strictly smaller than 1/2, it is a fractional power of the log. So in particular, this field H theta is not log correlated. So it is not possible to take the exponential of this field. And we also attend that this field is conformally invariant. This is just a direct consequence of the fact that the Brownian loop soup is conformally invariant. And also this field is symmetric, so that the minus H theta has the same distribution as H theta. So now let me give more details, give you some ideas of the proof, like how we actually construct this field. So because we want to show that this field is the limit of some field h theta gamma that we have defined, and we want to take the limit as gamma goes to 0. So we would actually try to take the limit of the second moment of h theta gamma integrated with some test function f. And by definition, this integral is written as some integral using the multiplicative chaos measure. And then we will use some lemma on the correlation of the multiplicative chaos measure. You see some rather complicated formula here. So for example, this line below, it looks complicated, but actually what it is saying is that in the case that there is no loop that visit both points x and y, then if you integrate some function f on x, y, and the local time field according to the multiplicative chaos measure, then it is the same as if you integrate according to the Lebesgue measure, but you add, because the multiplicative chaos measure is a measure on sig points of the loop soup. So it's like you add some additional thickness to the points x and y. So which amounts to adding some independent sets of loops rooted at x and y to that loop soup. So with this kind of lemmas, we are able to show that in this integral on the top, the contribution from loops that visit both x and y is small. So most of the contribution comes from clusters that visit both x and y, but not single loops. And then we will just compute this integral restricted to the event that there is no loop that visit both x and y in the loop soup, so that we can apply this formula where we add some thickness to the points x and y. And with all this complicated transformation, what we actually in the end want to obtain is that this second moment of h gamma f, it is roughly equal to this expression integral. So let me explain. So here this probability x connected to y inside loop soup union with two independent sets of loops rooted at x and y, which correspond to the thickness of at x and y. So our second moment is in fact very close to this expression of integral involving the crossing probability of the clusters in the loop soup. So you should think of these psi x and psi y, these sets of loops rooted at x and y, as small disks centered at x and y, because typically they will have some small radius around x and y. And then this probability that we have here is in fact the probability that there is a cluster in the loop soup that gets very close to x and y at the same time. And now in order to get a limit as gamma go to 0 of the second moment on the left, we need to first prove the following ingredient, is that this integral using the crossing probability converges. We need to show that this limit exists. And showing that this limit exists also will allow us to define a cluster conditioned to go through one point. So we actually show that if so for example, in the unit disk, if we take some eta to be some fixed macroscopic number between 0 and 1, and as epsilon to be some small number tending to 0, and let's see epsilon be the cluster in the loop soup that intersects both the small disk epsilon around 0 and the cluster with the largest diameter that intersects the disk around 0, epsilon around 0, then conditionally on the event that this cluster intersects a macroscopic circle eta, then this law C epsilon converges as epsilon goes to 0. So we are able to define a cluster condition to pass through one point. So this will enable us to show that the limit exists. And on the other side, we also get asymptotic estimate of this renormalizing constant C gamma as a gamma to a power 2 times 1 minus theta. And this will allow us to get a asymptotic expression of this correlation function, covariance function C xy. So in order to now focus on the second part of this crossing exponent of a cluster, and so we obtain that in a loop soup with any intensity theta subcritical, the probability that a cluster in a Brownian loop soup intersects both the microscopic circle epsilon and some macroscopic circle are the case like log epsilon to the power of -1 plus theta. And as you see, when theta equal to 1/2, this probability decays like log epsilon to the power of -1/2. This was already known. And when theta equal to 0, this probability decays like log epsilon to -1. This was already known like for one Brownian motion. See, so this is an interpolation between one Brownian motion and the Brownian loop soup of intensities, critical intensity. And I don't have time to go into the details of how we obtain this crossing exponent, but one thing that is worth emphasizing is that this exponent cannot be obtained using i.i.d. Because previously we have also have some very nice, we already know many exponents about the Brownian loop soup due to its connection to i.i.d. and s.i.d. Say like the boundaries of the outer boundaries of the clusters. But this is about the probability that a cluster goes close to an interior point. So in particular, that point will not be on the boundary of the cluster. So this cannot be obtained using i.i.d. And also this probability always decays as some power of log. So it doesn't, unlike in percolation, when you have a subcritical regime, your decay rate is much faster. So this, in this sense, this subcritical loop soup is not really a subcritical system. So with this, it's as a result on the crossing exponent, we were also able to show that clustering a Brownian loop soup with intensity theta almost surely has Minkowski gauge function t square ft for some function ft which which scales like log t to 1 minus theta plus little 1. And so now let me give you some conjectures which will give you some intuition. Yeah.
With respect to this Minkowski gauge function, is the actual measure the occupation measure of the loops?
Yes. So in fact, we expect that this Minkowski gauge function will be equal to this field edge theta restricted to that cluster. Yeah, and this is, I think, in the critical case, this was this is proved I don't know if it's written, but by Aru, Lupu, and Sepulveda in the critical case. But in the subcritical case, we expect that this is also true. And and you can see it kind of from the definition of this field, because it is from this crossing probability of at 2 points, right? So it's like the Minkowski measure. So now I show you some conjectures about this field H theta, which will give you more intuition on why it is the correct field linked to the Brownian loop soup by isomorphism, and what is this field. Okay. So our first conjecture is that we can construct this H theta from a discrete loop soup. So we first sample a random walk loop soup on a discrete lattice with some occupation time field. And then we would define a field where we just take the occupation time field and raise to the power 1 minus theta. And we also give it a sign, give i.i.d signs to different clusters of this random walk loop soup. And in front, we have some complicated renormalizing constant, but this is just not important. It's just, we take the discrete occupation time field, takes a fractional power of 1 minus theta, and give i.i.d signs to each cluster. So this is the intuition behind this field that we construct.
But previously you were saying that you'd like, in a sense, to take in the continuum, you wanted to take a square root of the occupation time. Now you take power 1 minus theta.
Yeah.
In the continuum, you had an intensity parameter. Here you don't have an intensity parameter.
So previously, I started the background by just talking about the critical loop soup. And in fact, isomorphism theory for the loop soup was only known in the critical intensity C equal to 1. For subcritical intensity, there was no, it was not established even in the discrete or any other. So as you see, when theta equal to 1/2, this power, fractional power will be 1/2, which is the square root. And so we show that, in fact, for any subcritical intensity theta, the correct thing to do is to raise to this fractional power 1 minus theta.
And the intensity doesn't matter on the discrete.
The intensity is theta, actually. Theta is the intensity.
But the loop soup itself is just any loop soup of any intensity in the discrete.
The loop soup has intensity theta. So we show that, yeah, we need to, I probably should add, like here, sample random walk loop soup on a discrete lattice with intensity theta.
Okay, that was.
Yeah.
Do you take the discrete simple walk or the diffusion on the edges?
It can be any version. Yeah. Anyway, this is still a conjecture for the moment, but we think it does not matter how you approximate the continuum. I think most discrete graphs, all the diffusion, they should work. So, yeah, so the idea is that it is a fractional power. And this actually took us a long time to realize the fractional power, because it was very natural to think that we always take the square root as the critical case. So this conjecture, I'll give you some justification of this conjecture. In fact, in the discrete, if we do take this fractional power and look at this series, define this series, complicated series, and then this series will actually converge to this m gamma plus in the continuum, jointly with the loop soup. So here Lxk is just local time raised to power k, And here, this part xk times this fractional power. So this integer power and the integer plus fractional power. This complicated series. So this, if we could prove conjecture 1, then we can also prove this conjecture 2, which gives a series expansion of the m gamma plus for theta between 0 and 1/2. And then, in fact, this conjecture 2, you can also, we can justify that it's a reasonable conjecture, because if we take m gamma plus and m gamma minus and add them up, we will get m gamma. And the first terms here, they like the even terms, they exist in both m gamma plus and m gamma minus. And the second part, they are like the odd terms which cancel with each other in m gamma plus and gamma minus. So the actual series expansion of m gamma would be just twice the first terms. And this, we can actually prove it. And this is also the analog of extension of this theta equal to 1/2 case, where you have the hyperbolic cosine of gamma h, and you also have such a series expansion on the local times of the loop suit. So this shows like why these both conjectures are reasonable, and like this field is intuitively a fractional power of the local time field. And now I guess I still have 10 minutes. So now let me go to some easier case where things become more intuitive, and you can see better why this isomorphism works for that fractional power. So let us now come to the one-dimensional case where everything's finite. Okay. So in dimension 1, the isomorphism theory at the critical intensity says that if you take a Brownian loop suit on the interval like 0 infinity with intensity c equal to 1, this will give rise to an occupation time field T1, which is distributed as 1/2 the square of Brownian motion. So it is also equal to the square Bessel process with dimension 1. And then we also know that there is the additivity of the occupation time fields of the Brownian loop suit, just because it's a Poisson point process. So if you take the occupation time field intensity C1 and then C2, you get intensity C1 plus C2. But we also know the additivity of square Bessel processes for different dimensions. So it is, we can deduce then that in fact TC is just equal to a Bessel, square Bessel with dimension C. And this can be checked by directly computing the characteristic functions. That was done by Le Jan and okay. So the occupation time field of a one-dimensional loop suit is equal to a square Bessel, like for that, where the dimension is equal to the intensity of the loop suit. And for C between 0 and 1 subcriticals, the square Bessel, it hits 0 infinitely many times. And for C bigger than 1, the square Bessel never hits 0. So it corresponds to the phase transition where the loop suit form infinitely many clusters or only one cluster. Naively, if you sample square Bessel and then take the square root and then give i.i.d signs to each cluster, then you get some kind of a Bessel process with dimension C. Okay, I say reflected at 0, but not really because I make some policy. Sorry. So naively, this is what can make you think at first that you should take the square root because in dimension 1, you get Bessel. But in fact, surprisingly, the correct thing to do is to take the fractional power, like not a square root for general C. So one reason to see why the fraction power is good is, so if let x theta be a square Bessel process with dimension 2 theta, and x is distributed as occupation time field of the loop with intensity theta, and let h theta be obtained from x by taking the power 1 minus theta, and then choosing i.i.d signs for each cluster. A cluster in D1 is just excursion of the Bessel process. And then we can show that if we take any bounded measurable function f of this field T, this occupation, probably I should put x theta here of this field x theta and weight them by h theta x and h theta y, then you will get like some dual Bessel process. It's with a dual dimension theta star equal to 2 minus theta, and with some constant terms in front. So it means weighting by this field h theta is like change at points x, y is like changing the dimension of the Bessel process on the interval x, y to the dual dimension h theta star. And we expect some analogous relation of this type to be true also in dimension 2. So it is still some vague, but I hope convincing reason why this is the correct thing to take the fractional power. So
Why do you say dual intensity? Here critical intensity is theta equal a half, theta star is, so at the critical intensity theta half is 3/2, it's not so. What are you saying?
Yeah, the dual intensity is super critical. Yeah. Yeah. So in fact, here in the first expectation, in order to have some non-zero thing, I think you need x and y to be in the same cluster. Otherwise, they take independent signs and you'll get 0. This is why it's like making the intensity on the segment xy to be the dual intensity, which is super critical. So they almost surely lie in the same cluster. This is all, and thank you for your attention.
Any questions?
Yeah.
What happens in dimension 3?
Yeah, we haven't thought about. I guess like this isomorphism should be true also in, because the critical case, the isomorphism holds in dimension 1, 2, 3. And this we already know in dimension 1 and 2. So I would expect that it also holds in dimension 3.
And it's something accessible?
Probably. It's a good question. We have not thought about dimension 3.
So what happens in dimension 4? What goes wrong?
For the critical case, for example, the square of the Gaussian field is not like well defined, like the weak square in the continuum is not well defined for dimension 4. And I know that it's possible to do some extra renormalization procedure probably to define the square in dimension 4. But that dimension 4 is also kind of some critical dimension where for dimension even higher, I think, I don't know, maybe that even no good way to define the square. But I don't, that's what, yeah, my impression. Maybe someone knows better than me. So the loop, for example, occupation time field of the loop soup to make it well-defined in the continuum. In Le Jan's argument, he uses some determinant 2 for some operator, like, but in dimension 4 or higher, even determinant 2 is not enough to, maybe you need to take the depth 3, but then it, yeah, I don't know.
A very vague question. Here your fields are built out of Brownian loop soup, so Brownian motion is very canonical. Any notion, I don't know how exactly to create a GFF loop soup and create something out of that?
What is GFF?
Yeah, that's the question.
It's level 1, I don't know.
So maybe you can have like two-dimensional surfaces that are in the same
Oh.
dimensional space. You create an occupation time, you create something out of them.
Like 2-dimensional loops.
Yeah, well, it might be have a fractal dimension, it's even higher.
Yeah. So Xin, you also had a.
Yeah, can you compute any correlation function for this H theta?
So for the moment, what we know is this C theta equal to log, like asymptotic is this log.
So can you remove this little one?
Yeah, for the moment, we cannot remove it. Yeah.
But you know it exists, okay.
We expect that there should not, like for theta equal to 1/2, yeah, because it's the Gaussian free field, there is no little one. But for theta smaller, for the moment we cannot.
I think there's also something on the chat. So there's a question.
I cannot see. It disappeared.
I think if you maybe you click arrow, like, oh, there's nothing, okay. Maybe it's not archive. Any other questions? Okay, if there's no questions.